Hey everyone, and welcome. Have you ever just stopped and looked around at how everything, well, moves? I mean, from planets swirling around the sun to just you walking down the street. Motion is happening all the time, everywhere. But what are the rules behind it all? That's what we're going to dig into today.
Right. That's the big question, isn't it? For centuries, this puzzle had even the greatest thinkers scratching their heads. But then, this absolute genius, Sir Isaac Newton, came along and basically laid out the universal rule book for motion. 3 simple laws that changed everything. And in this explainer, we're going to break them all down. But before we can jump into the laws, we have to meet the main character in our story, something called a force. You can think of it as the invisible hand that makes everything happen in the universe of motion. So, what exactly is a force? Well, at its heart, it couldn't be simpler. It's just a push or a pull. That's it. But that one simple idea, that push or pull, is responsible for pretty much every change in motion you can imagine. It's the cause, and the movement is the effect. And you can see forces literally everywhere. Pushing a shopping cart, a hockey player smacking a puck across the ice, or even something as simple as squeezing a rubber ball. All of these are examples of forces at work, changing how an object is moving or even just changing its shape. Okay, so here's a really crucial idea. Forces come in 2 main flavors, balanced and unbalanced. Balanced forces are equal and opposite, so they just cancel each other out. Think of a tug of war where nobody's winning. Nothing really changes. But unbalanced forces, that's where things get interesting. When one force is bigger than another, that's when you get a change in motion. And this little diagram is a perfect way to see it. In those first 2 pictures, the kids are pushing, but the force of friction is pushing back just as hard. The forces are balanced. The box is going nowhere. But then look at the third one. They push harder, creating an unbalanced force that's stronger than the friction, and bam, the box starts to move. That right there is the key. Change only happens when forces are unbalanced. Okay, now that we get what forces are, we're ready for rule number 1. Newton's first law basically describes the default setting for every object in the universe. It's also known as the law of inertia. Now, that's the official version. It sounds a little formal, I know, but the idea behind it is super intuitive. It basically says that things just keep on doing whatever they're already doing. If something is sitting still, it's going to stay still. And if it's moving, it's going to keep moving at the exact same speed in a straight line. And this resistance to change has a name: inertia. You can kind of think of it as physical laziness. Objects just don't want to change what they're doing unless an unbalanced force, that push or pull we just talked about, comes along and makes them. And here's the most important part about inertia. It's all tied to an object's mass. The more mass something has, the more inertia it has. It's exactly why it's so much easier to get an empty shopping cart moving compared to one that's full to the brim. The full cart has more mass, so it has more inertia, and it resists you that much more. Oh, this is such a great little experiment. It shows inertia perfectly. When you flick the card, the force acts on the card, not the coin. The coin's inertia, its tendency to just stay put, leaves it hanging in the air for just a split second. And with the card gone, gravity just takes over and pulls it straight down into the glass. And if you want an example you've definitely felt, just think about being on a bus. When the bus suddenly stops, what happens to you? Your body wants to keep moving forward because of its inertia. That sudden lurch you feel? That's Newton's first law happening to you in real time. So the first law tells us what happens when forces are perfectly balanced, which is nothing changes. But what happens when they're unbalanced? Well, that brings us to Newton's second law. This is really the mathematical heart of all motion. So the logic kind of flows like this. An unbalanced force causes an object's velocity to change. In other words, it makes it accelerate. And the amount of that acceleration depends on just 2 things: how much mass the object has and how big the force is. This simple relationship gives us one of the most famous equations in all of science.
F equals ma. Force equals mass times acceleration. This little equation is so powerful. It tells us exactly how much something will speed up, slow down, or change direction based on its mass and the force you apply to it. If you want more acceleration, you need a bigger force. Or if you have a bigger mass, you're going to get less acceleration from that same force.
And here is a fantastic practical example of the second law. Why do you see a cricket fielder pull their hands back when they catch a super fast ball? By pulling their hands back, they increase the amount of time it takes to stop the ball. They're decreasing its acceleration. And if you look at F equals ma, if you make the a smaller, you make the F, the force, smaller too. It's a brilliant bit of physics that makes the catch hurt a whole lot less.
All right, we've talked about the law of no change and the law of change. The third and final law shows us this really deep and beautiful symmetry in the universe. It turns out forces never, ever act alone. I'm pretty sure you've heard this one before. It's so elegant, so simple, but so profound. It means that anytime one object pushes or pulls on a second object, that second object is pushing or pulling back on the first one with the exact same strength, just in the opposite direction. Now, this is the most important part, and it's the bit that people sometimes get confused about. This action and reaction pair of forces, they don't cancel each other out. Why? Because they're acting on two different objects. That is the whole key. Okay, let's look at the action forces in these pictures. On the left, you've got the gun pushing the bullet forward. That's the action. On the right, you see the sailor's feet pushing his body forward so he can jump. That's the initial action. And here are the reactions. At the exact same moment the gun pushes the bullet is pushing the gun backward. That's the recoil. And as the sailor jumps forward, his feet are also pushing the boat backward. Two forces, equal in size, opposite in direction, but acting on two different objects. That is Newton's third law. So there we have it, the law of inertia, the law of acceleration, and the law of action-reaction. These three simple rules work together to explain every single push, pull, and movement in our physical world. Let's just wrap it all up. The first law, inertia, is why your seatbelt is so important. It provides the force needed to stop your body from continuing forward when your car stops suddenly. The second law, F equals ma, explains why a light sports car with a big engine can accelerate way faster than a heavy truck. And the third law, action-reaction, is literally rocket science. The rocket pushes exhaust down, that's the action, and the exhaust pushes the rocket up, that's the reaction. You know, from kicking a ball to just standing on the ground, these laws are happening all around you all the time. They aren't just some abstract rules in a physics textbook. They are the script that the physical world follows every single day. So my question to you is, now that you know the rules, where are you going to spot them in action? Thanks so much for watching.